Hi, welcome to another session of Circuits and Networks. In today's class 3, under three-phase circuits, we are going to see some of the basic problems and solutions which are involved with three-phase system. If at all you look into the engineering background, especially EC students, triple E students, and some of the CSE and IT students, they find quite difficulty in understanding the single-phase system and three-phase system. Today you follow the approach which we are going to employ in order to solve three-phase circuits. Then you can look into the single phase system, how they can be solved. First, you try to understand the problem in detail and then see the technique, how the formulas are employed in order to get the solution for a particular problem. Here you can see a phasor diagram representation of a three-phase system and a three-phase system which is connected as star to star network where you have sending end and receiving end, and it's a three-phase four-wire system. So most of the problems are involved with star to delta and delta to star problems, or star to star and delta to delta problems. So the basics of this star and delta are already we have seen in our class 1 and 2, and in our today's class we are going to see some more numericals which are involved with three-phase system. So in the first problem, an input of 440 volts 50 hertz is applied across a star connected load. If the three coils of that load is having 4 ohms and an inductance of 0.1 Henry respectively, then find the active and the reactive power of the system. So we are assuming that 4 ohm is in series with 0.01 Henry. So if at all we start with the solution, we are taking the input data whatever it is given to us. We have voltage, line voltage, which is as 440 volts. This is also known as the RMS value of the input voltage, and frequency it is given as 50 hertz. Then let us find out the XL value. Why XL value? Because the resistance value is in ohms and the inductance value is in Henry, and we can convert Henry into ohms by having the inductive reactance formula, which is given by XL, which is equal to omega L. Omega is known as the angular frequency. It can be changed into the normal frequency with the help of formula of omega is equal to 2 pi f. So 2 pi f multiplied with inductor value. So here you have 2 pi. The pi value is here, it is 3.14. You can take the help of your calculator and you can substitute these values. Frequency it is given as 50 hertz and the inductor value it is 0.01. So just substitute the value. We are going to get the inductive reactance, which is in ohms. The value is 3.769. Now once we are done with this inductive reactance, let us calculate the overall impedance of the circuit. The overall impedance of the circuit, it is a combination of the real component and with the imaginary component. So it is given by R plus JXL. So the R value is 4 ohms, and just now we estimated the value of XL, which is 3.769, and J, it is the imaginary component. So the impedance value of this particular star connected load, it is in rectangular form. You can change this rectangular form into polar form with the help of your calculator or with the help of the normal calculations of the mathematics. So you can convert the rectangular form to polar form. So the polar form value of this particular impedance is nothing but 5.495 at an angle 43.29 degrees. Hence, we have obtained the impedance value in magnitude form as 5.495 ohms, and the phase angle between voltage and current, it is 43.29 degrees. So once we are done with these two values, let us calculate the power factor. The power factor is given by cos phi. That is the angle between voltage and current. So the angle which we got here is 43.29. So cos of this value is 0.7278. Once we are done with this power factor, we can easily get the value of the sine form of the angle. Why we are doing this? Because we also wanted to know the reactive power of the system. For that we require the sine of phase angle. So the sine of phase angle value is 0.6856. So once we are done with the power factor value as well as the reactive power component value, one of the component value, that is sine of the phase angle value, Let us calculate the voltage of the phase. So the voltage of the phase for star form is nothing but VL by root 3. So VL value is 440 ohms, sorry 440 volts divided by root 3. The value is 254 volts. So that is the phase voltage of the star connected network. Now the phase current, which is nothing but V phase by Z phase. The value of V phase is 254 and Z phase, the magnitude value we got as 5.495. So we are going to get the value of phase current as 46.23 amperes. In fact, in star network, the phase current and the line current, they are one and the same. Now, the active power of the system is given by root 3 VL IL cos phi. So root 3 substitute as it is. The VL value is nothing but the RMS value, that is 440 volts. IL value is equal to I phase value, which is 46.23 amperes. And the cos phi, that is the power factor value, we got here as 0.7278. So overall the active power we got here is 25.64 kilowatts. Similarly, we can get the value of reactive power, whose value is given by root 3 VL IL sin phi. Substituting the values of VL and IL and sin phi, we are going to get the value of reactive power as 24.158 kilovolt ampere rating. The reactive power units are in volt ampere rating. So this is how we can easily solve the three-phase system problems. Let's go with another example. Especially here we have a delta connected load. Each phase is consisting of 40 millihenry inductor in series with a parallel combination of 10 ohm resistance and 50 microfarads capacitor. What does this mean? You have 40 millihenry connected in series with a parallel combination of 10 ohm to 50 microfarad capacitor. For that kind of load, we need to find out the reactive power. If the load is connected to a supply, input supply is here, it is given as 440 volts, and here you can see the angular frequency value is given, which is nothing but 1000 radians per second. We are dealing with AC circuits. So this is how each leg of the delta load will be like this. So you have inductor connected in series with the parallel combination of resistance and capacitor. Okay, so the data which is given as the input voltage VL, which is 440 volts, omega is 1000 radians per second, inductor value is 40 millihenries, resistance value is 10 ohm, capacitance value is 50 microfarads. With this I can get the value of inductive reactance, which is equal to omega L. So directly we are substituting the angular frequency value, that is 1000, multiplied to L, that is 40 millihenries. So I'm going to get the value of XL, which is equal to 40 ohms. Similarly, XC, which is equal to 1 by omega C. So the value of omega is 1000. C is 50 micro. So when micro goes to the numerator, it becomes 10 to the power of 6. This value will be equal to 20 ohms. Now once inductive reactance, capacitive reactance are obtained, we can easily find out the value of impedance of the circuit. So the impedance of one leg will be equivalent to J omega L, because inductor value is here in reactance form, plus resistance multiplied with the capacitance. So the resistance value in the terms of the capacitive reactance, it is given by R multiplied with minus JXC divided by R minus JXC. So just substituting the values what we got over here. So 40J plus 10 multiplied with minus 20J divided by 10 minus 20J, which will give you the value as 8 plus 36J, or this rectangular form can be changed to polar form as 36.87 at an angle of 77.47 degrees. So once we are done with the impedance value, that we got the value of impedance in magnitude form and in angle form, the value of phase angle is 77.47. So the power factor would be cos of this phase angle, which is will be equivalent to 0.216. And just for the reactive power value, we are converting the phase angle for sine term as 0.6856. Now for the delta network, the voltage of phase and voltage of line are are same. So that is why the value of line voltage is equal to 440 volts and I phase is equal to V phase by Z phase. So 440 divided by 36.87 will give you the value as 11.93 amperes. But in delta network, I phase is equal to IL by root 3. So the value of line current will be equivalent to 11.93 multiplied with root 3, whose value will be equivalent to 20.67 amperes. Once we are done with the values of voltages and currents in phase form and in line form, we can easily form the formula for active power, which is equivalent to root 3 VLIL cos phi. Substituting the values, we are going to get the value of active power as 3.4 kilowatts. The reactive power will be 10.8 kilovolt amperes, and the value of apparent power, just neglect this cos and sine terms, then we'll get the value of apparent power, whose value is 15.75 kilovolt amperes. Whether we got the value correct or not, you can take the uh, values of a power triangle and you can substitute the values for power triangles. You'll get the match of active power and reactive power, which is equivalent to the apparent power. So I think now it is simple for you how to solve the problems for active and reactive powers for three-phase system. In order to give a particular conclusion, let us go with another example. Same, I'm taking the input voltage as 440 volts, 50 Hz three-phase AC input is applied to three star-connected identical impedances. Each impedance consists of resistance of 20 ohms, inductance of 0.2 Henry, and the capacitance also given as 180 microfarads. All are connected in series. Means what? Resistor, inductor, and capacitor are connected in series. We need to find out active and reactive power. For that, just taking the inputs and calculating the value of inductive reactance, which is 60.83, capacitive reactance as 17.68, and finally the value of impedance, because all are connected in series, so the value will be equivalent to R plus JXL minus JXC. Substituting the values, I'm going to get the value of impedance in magnitude form as 54.92 ohms, and the phase angle between voltage and current will be 68.64 degrees. Now the power factor value is obtained to be 0.3642, and the reactive power, for reactive power, the sine term will be equal to 0.931. Now I phase is equal to V phase by Z phase. So substituting the value of V phase and Z phase, we are going to get the value of I phase as 4.649 amperes. Since we are dealing with the star network, we have to keep in our mind that current of line and phase will be the same. So the value of the active power will be 1.29 kilowatts and the reactive power will be 3.29 kilovolt amperes. You can calculate the apparent power. Now what if the same problem it is given in delta form? So all the values are same, just the connection is changed to delta. So we need to keep in our mind that in delta connection, the line voltage is equal to phase voltage. So both the values are the same. And just now we estimated the value of impedance in magnitude form as 54.92. So the I phase will be equivalent to 8.011 ampere. Now in delta network, I phase is equal to IL by root 3, so that the value of line current will be 13.875 amperes. So once we are done with this value, we need to calculate the active and reactive power. So the active power would be equivalent to 3.85 kilowatts. So for the reactive power, please solve by yourself and comment in the chat box whether you got the reactive power or not. So for these kind of problems, please stay connected to our channel and please share among your friends, subscribe to our channel and please press the bell icon.